parallelograms in reverse. Aha! That is actually what we're going over today. Now, what do I mean by that? So, in our previous sections, we've been given as our starting point this shape is a parallelogram, this shape is a rectangle, and then asked to prove something based on that, or solve for a variable based on that. Today, we're going to do the opposite. Starting from some given information, we're going to show that a quadrilateral is a parallelogram, or more specifically, a rectangle or rhombus, perhaps. So, remember those theorems about parallelograms that gave them their special properties? Turns out that they all have true converses. This means, for example, that if we can show that a quadrilateral has two pairs of congruent opposite sides, then that shows it's a parallelogram. And the same is true for all of these others. We'll use this in proofs like these. Now, proofs are difficult to do as an ed puzzle, especially when, as with part A here, they need a little bit of assistance in the form of an extra line. So what I'm going to do instead is I'm going to ask you which triangle congruence shortcut you think we're going to use as part of the proof for part A. Let's see if we agree. Now we know that EF is congruent to GD because it's given, and DE is parallel to FG because it's given, and GE is congruent to itself because I drew it that way, and the reflexive property, of course. Well, that gives us a pair of sides, and a pair of sides when we're talking about congruent triangles, and we've got some alternate interior angles. Let's see, DGE is congruent to angle FEG. There's a pair of angles. And so I've proven this with side angle side. Then with CPCTC, I can say that DE is congruent to FG, and that means that we're done. DEFG is a parallelogram because opposite sides of a parallelogram are congruent. So how about part B? That one might be simpler, perhaps? Certainly seems to me. So Alan and Daniel are congruent, and so are Anil and Dylan. Gives us, oops, that's completely wrong. So that's two pairs of angles. And then, as you've hopefully noticed, we also have ln being congruent to itself. Which is a pair of sides. So we can say that these triangles are congruent. By the SAS postulate. Then we can use CPCTC to say either the sides or angles are congruent, though the sides are simpler. And then together, that tells us that land is a parallelogram. Because once again, the opposite sides are congruent. Now, as you've seen, mostly though, we're going to do more algebra. Now, this problem right here looks just like one of the problems that we had on our previous assignments. The difference being the way the instructions are phrased. Previously, they would say, EFGH is a parallelogram. Solve for x and y. In this case, however, they're saying, for what values of x and y must EFGH be a parallelogram? It's a different idea, but in practice, it's exactly the same. So why don't you take a moment and find out what x and y happen to be, so that they make EFGH a parallelogram. Let's see, that's 25 plus 18, so that would be 43? Yeah, that's 43. And then there's several ways we could find x, but I'm just going to do it the same way. Huh. Guess I should have solved for x first. That was much easier. So, that's pretty much it. The same is true for the converses of rectangles and rhombi. Their special properties can also be used to prove what they are, though usually the problems will be phrased such that we already know they're a parallelogram. And mostly, as in the same case, we'll be doing more algebra. So let's try and find x and y for these two problems. Since the diagonals of a rhombus bisect its angles, that means that if ABCD is to be a rhombus, then those two must be equal. And I think that's going to be 5. And in a rectangle, the diagonals bisect each other and are equal. So these must once again be equal. Looks like y equals 4. All right, so there we have it. So I'll see you next week.